Okay, well, thank you very much for inviting me, and thank you very much for this very honorful introduction. I will present the Stochastic Actor-oriented Model, and in the course of my presentation, you will hear what it is. And this is a model for network dynamics, which really is in the paradigm of classical statistical inference. So it is, I have tried in some of my work to really combine social network analysis with classical statistical inference, with hypothesis testing and estimation and goodness of fit testing, etc. And the start of my presentation is a conceptual overview. And after that, I will treat two examples extensively, and you will. But I will start with an overview, which is a conceptual overview and not so much a technical overview. So the technical overview are left for other opportunities. Oh no, I have to see. I think. Okay. Okay, the conceptual overview. So the stochastic actor-oriented model is a model for studying social behavior in a context, so context dependence in social situations. And it's clear that in social situations, we are linked to others. We are not monadic individuals. So networks are the good representation of that. And our behavior is context dependent. So it's influenced by others and by the opportunities that are offered by the context. And this behavior is changing our own context, but it's also changing the context of the others. And in the same time, the others are behaving and changing my own context. So this leads to a feedback process of the activities and the choices of self and everybody else. And it's clear that this feedback process and this contextual approach contrasts with the classical mainstream statistical approach in which everything is based, well, think of regression analysis, everything is based on the assumption of independent residuals. So the question is, how can we investigate this contextual, context-dependent behavior? The units are not independent, and variables are explanatory and dependent at the same time. So we can no more talk about dependent. We are in regression terminology. We are used to talking about dependent and independent variables, but we really should think not about independent, but about explanatory variables. However, each variable might be dependent and explanatory at the same time. And that can be analyzed, I would say, only in a longitudinal context. So you really need to go away from cross-sectional data and cross-sectional modeling, but you need longitudinal modeling. And the stochastic actor-oriented model has a probability model, which expresses these context-dependent choices. And if I may separate the probability model from the statistical model for estimation is based on panel data. And so network panel data are data in which you've got a network and perhaps other information, which is observed sequentially at 2 or more occasions. So when I say longitudinal data, then I'm starting with 2 repeated observations of a network. With 2 repeated observations, I'm already, in my mind, I already have longitudinal data. So we have a system, think of the feedback idea, a system with a changing state. And the system exists at the least of one network, and I differentiate between one-mode networks and two-mode networks, and one-mode networks are the usual type of networks to which you are accustomed. A two-mode network is a network from nodes in one set A to nodes in another set B. And for example, for the set A, you can think of individuals, and for the set B, you can think of activities. And for example, clubs, where do the individuals hang out? And then we've got a two-mode network of individuals and clubs. Or you can think of sport, what are the sport activities that the individual do? And then you've got a two-mode network of individuals and sports. Dependent variables can also be individual behavioral tendencies of actors, like smoking or drinking, pro-social or antisocial behavior. So we can both have networks as dependent variables, which may be one mode or two mode, as well as actor-based characteristics like health-related behaviors like smoking, or social-related behavior like antisocial or pro-social behaviors. And the simplest case of this model is with one complex dependent variable, like one mode network. But it becomes really interesting when you've got several dependent variables, like a one mode network and a behavior variable, and perhaps a two mode network or several one mode networks. And then we speak of co-evolution, so the joint dynamics. Co-evolution is a word that is used in many different sciences in different ways. For example, biologists speak about the co-evolutions of humans and dogs, because in the past 30,000 years, wolves were, anyway, I shouldn't say this, but you can think of wolves turning to dogs slowly while being in interaction with humans. And that's the co-evolution. For biologists, co-evolution is something, with example, co-evolution of humans and dogs. But for me, co-evolution is a co-evolution, for example, between a friendship network and alcohol drinking. When we have, I would like to make a little step aside back to cross-sectional modeling. And in networks, we've got the exponential random graph model, the ERGM, as a well-known cross-sectional network model. But when you apply a cross-sectional network model like an ERGM or a stochastic plot model, then you make the implicit assumption, or explicit, that the system is in equilibrium. And I think that that assumption often is wrong, and it hardly ever can be really checked. And I think networks come about by any ways in the past. So a current network may be in flux and you don't know where it came from. So I think single one-shot observations of social networks don't tell you very much about social process, social laws, let's say, the social regularities. So I think you need a longitudinal approach to social network analysis. In what you mentioned, Kagoi, in the past, I've made a number of contributions to ERGMs also, but so I've concentrated on longitudinal modeling because I believe that is more fruitful for sociology and for progress in sociology. And as I said earlier, I'm considering panel data where the paradigmatic example is that as a researcher, you go into a school and you ask everybody in the school who to mention their friends. And you do that now, and you do that a year from now, and then perhaps 1 year later again. So that is an example of panel data, network panel data. The longitudinal models need to make certain assumptions, and one basic assumption is the Markov property, and that is that when we are talking about a system with a state that is changing, so we are not talking about networks of telephone calls, which are events, but we are talking about networks like friendship, which are longer lasting, although they can change and they will change. But they don't change just like that, and they don't change easily. For a network system to be able to manage it in a statistical way and do statistical simulations, it is very convenient to assume the Markov property that the probabilities of change depend on the current state of the system and don't depend on how you got there. But so all the information that you have about the system can be contained in the current state. And as a matter of fact, in many agent-based models, which are not of the statistical kind, nevertheless, this assumption is made that you've got a state, and that state determines the probabilities of change. For statistical models, moreover, you must be able to observe the entire state. So you must be able to observe all the networks, and if there is a mental state, then that mental state of the agent might be used in agent-based models. But if mental states are not observed, then you cannot use them in the kind of statistical models I'm talking about. To be able to simulate them, I made the decision when I started all this that the first wave, so think again of two waves, two panel waves, the first wave should be used just as the starting point of the simulations. And you don't use the first wave to get information about any parameters of the model. The starting point, the first wave, is just used as the starting point, whatever it is. And the statistical way of saying this is that we condition on the starting point. And if you've got a Markov system and you've got a starting point, then you can simulate it. Think of a network and think of a changing network, then of course changes in the ties in the network are interdependent. And the Holland and Leinhardt already in 1977 made a very important proposal that they said to study a changing network, you can assume, even with panel data, you can assume that unobserved, there is a continuous time process in which all kinds of changes occur after each other without being observed. Think of a friendship recorded now and recorded in the future a year from now. In between, friendships can stop. New friendships can be created. And the actors are aware of that in reality, but as a researcher, you don't observe it. However, in the simulations, you can simulate it if you've got the model correct. So the stochastic actor-oriented model assumes that even though we've got discrete time observations, like only two, nevertheless, the probability model takes into account changes at random moments in between the observations. And also, the assumption is made that at any moment, if a change occurs, only one type variable can change. So only one tie can be created or one tie can be dropped. That means that the dependencies between the network ties are created sequentially rather than by coordination. And so it is a reactive dependence. In the model, for having a nice, convenient word to talk about them, I call those changes mini steps. So in between the observations, many mini steps are taken, and at each mini step, one of the actors gets the opportunity to make a change. If the actor is satisfied with the current situation, no change is made, but else one new tie can be created or one tie can be dropped. And since there is no coordination, the actors, if there is a change at any moment, there's only one actor who will make the change. So you can have this kind of schematic representation. An actor, given dependent on the network, makes a change, and that will create the new network. And then for the next mini step, a new actor or the same actor randomly makes a change. For the model, we need the assumption of changes, so we need changes. And the basic model used here are choices. The change is a choice from a finite option set. The change model is easily brought in line with goal-directed behavior. I say this in a moderate way. It doesn't assume goal-directed behavior. The network is assumed to be directed, so actors have outgoing ties. They don't have control over incoming ties. That means they don't have control, they don't decide who likes them, but they only decide whom they like, who are there, they can mention their friends, whom they think, according to themselves, are their friends. For this model, the choice model is of that kind that the number of actors is usually between 20 and 2,000. And 2,000 really is at a very large side, because when it is more than 200, I think the model is implausible, because the choice is made from this set of all actors. And so if you think there is a person, an actor who makes the choice, this actor is choosing between all the options of actors in the network, all ties that might be dropped and all ties that might be created, and which are compared to each other. And if you think of having 200 choices, 200 options in mind, that is already huge, let alone more than. So I have said here 2,000 because I know that there are applications of, let's say, about 1,000 actors. And there you can you can not structure the choices, but inform the choices by having some knowledge of meeting opportunities. I will skip some of it because I need my time. So the basic idea is that actors control their outgoing ties, and the probabilities of tie changes are dependent on the so-called evaluation function, and the evaluation function can be roughly interpreted as the evaluation by the actor of the situation that obtains if this. So the evaluation function is a function of the state of the whole system. The model is based on two components. One component is the rate of change. Since it is a continuous time model, you need something to tell you when changes occur, even if it is at random moments. And for example, it might be the case that one actor makes more changes or makes changes more rapidly than another actor. And the second component is if an opportunity for change occurs, which choice will be made? So the probabilities of changes, if an opportunity occurs. And those two components are modeled by so-called rate functions and evaluation functions. And so schematically, the model the model step, so the mini step can be generated, can be pictures like this. A time increment is generated, then an actor is chosen who makes the mini step dependent on the rate functions. Then if this actor is chosen, the actor chooses the option to choose. This change is put into effect, and then you return to the next mini step. So this is one mini step, and between observations, each actor, well, in regular applications, it is common that actors will make, let's say, 2 to 10 mini steps per actor. So if you've got 50 actors, then you will have hundreds of mini steps to bring you from one observation to the next observation. For the rate function, usually we don't do very much, and we just assume constants. It is different if you have corporate actors where some big companies may pay more attention to the network and to their position in the network than small companies. So then you give actors differential rates, but for most networks between humans, you just don't think about the rate function, and it is just a constant, an unknown constant. For the evaluation function, we have, as I said, so the evaluation function defines the probabilities of change. If the current network is X, and X plus or minus ij is the network in which, the xij, so I have in mind the adjacency matrix of the network. Xij, so the choice from I to j, which is binary, 0 or 1, is toggled into, so 0 is changed to 1 or 1 is changed to 0. And that, given the network X, that is the hypothetically new network X plus or minus ij. And we define X plus or minus ii as the network X itself. And then this multinomial expression is the expression for the choice probability, where, well, you see the multinomial form, and the multinomial form is chosen because, well, it is in line with myopic stochastic optimization. Those of you who know this will say, yes, yes, I know, and those of you who don't know can take it for granted. The basic idea is that if the evaluation function of the new state, X plus or minus ij, hypothetical new state, is higher, then you've got a higher probabilities of going there. Then this evaluation function is, like we are used to in statistics, a linear function of explanatory variables, which we call effects because they depend on the network or other dependent variables in the co-evolution process. The main point of modeling is to define the effects in a given, so to select the effects in a given application, which are in line with the theoretical questions and what is known about the network dynamic process. And later on, we shall see a few examples, and you will see the kind of effects that are used. This is just an overview of three very elementary effects: the number of outgoing ties, and the effect, so-called the out-degree effect, the number of outgoing ties, the parameter, so the parameter beta with which this effect is multiplied. The parameter of the out-degree effect gives the balance between creation and dropping of ties, because with the creation of ties, the out-degree will become one less, and with the tie drops, the out-degree will decrease by one. Then the second base is the reciprocity effect, the number of reciprocated ties. Remember that it is actor-oriented. So this is the actors make the decision. So this is the out-degree of I, and it's the number of reciprocated tie in which I is involved. And the number of the transitive triplet effect is the number of triplets like this, friends of my friend are my friends, in which actor I is involved. For covariate, we need to make the transition from monadic to dyadic. So covariates, if they are actor bound, actor attribute, and the primary transformation from monadic to dyadic is ego, so the sender alter the attributes of the receiver, or similarity or same, this identity between the attributes of ego and alter. This is the overview of the ideas behind the stochastic actor-oriented model. Siena is the package that implements this simulation investigation for empirical network analysis. And when I coined the name Siena, later on I was very happy for that, because it's a brand name and people remember brand names, and they will often call this the Siena model, whereas really the proper name of the model is SAOM, which you cannot pronounce. Okay, this is the overview. Now I will give a brief introduction into co-evolution. So co-evolution of a network is of multiple variables, multiple complex variables, is joint interdependent dynamics of complex variables in which they will influence each other. And for the choice from, since all this was set up for choices from finite option sets with this multinomial logit, it works very nicely for discrete actor covariates, where the basic idea is that if the discrete actor variables is not only discrete, but also ordinal categories, then the mini-step will be defined as moving up 1 unit or moving down 1 unit in the ordinal scale, if you're not at the extremes. And all that works very nicely. And so the idea of network behavior co-evolution has led to a large literature on selection and influence. For example, for smoking, it is well known that friends of smokers tend to be smokers. And is that because smokers choose smoking friends, or because they influence their friends to smoke? And those questions can be answered by this technique. but my focus will be on co-evolution of networks. And I will drop this slide and I will go right to one mode, two mode co-evolution. And there so think of the example of a one mode network, which is a friendship network between individuals, and a two mode network, which is a sport network, the sports they do. When doing the sports, you can make friends, but you can also influence your friends to do the same sport as you. So the basic idea of influence and selection also can be seen in one mode, two mode co-evolution. There, in these pictures, the circles are the individuals in the first mode. Squares are activities in the second mode. Straight lines are one mode ties, so friendship. These wiggly arrows are choices of activities. And here you see the same end result of a closed triangle, but you see that in the top, it goes by both doing the same activity and then becoming friends. And here being influenced, as it were, by the friend to do the same activity. And the top can be called affiliates. If the two-mode network is, as the term affiliation, the top can be called affiliation-based network closure, and the bottom can be network-based affiliation closure. So the question then is, for which of these two processes do we see evidence? And I will discuss two empirical examples of this, and both are multi-level examples, that is many groups example. And the first one is a bit similar, although still different from the chapter I wrote with Christian in the handbook of rigorous sociology. And here I've got a micro-macro idea here. And the theoretical proposition are that friendship cliques, so a clique is a group of actors in a network who all have ties to each other, so in all directions. So in a three clique, you've got 6 ties. Okay, I'm not going to give the numbers because then I would have to count in my head. But so a clique, the definition is it's a maximal subgraph of a network with density 1. And think we are talking about directed networks. And maximal in the sense that if you would add a node, then it would no longer be a clique. It would have no longer density 1. And so the theoretical proposition is a friendship clique is supported by a common activity, at least one common activity. And the basic idea that expresses the basic idea of friendship, that you do some things with your friend. And the macro level property expressing this is the number of activities shared by all clique members in a given network, averaged over all cliques of size 3 and larger. Yeah.
I guess you exclude overlapping cliques on, like 4 clique could overlap a 3 clique, right?
Then the 3 clique wouldn't be a clique because it's a maximum.
Yeah,
so I only consider maximal cliques. Okay. And if 2 4 cliques would have an overlap, I count them both.
Oh, okay. Yeah.
Okay, and so this is the macro level property, and the micro level mechanism is what I just mentioned. So the combination of these 2 types of closures. And the data that I will be using, I got in collaboration with the group in Cologne. Clemens Kronenberg and Mark Witek, who have this social bond school survey. And they are just in the process of cleaning these data. So I'm proud. I don't know if this is perhaps the first application of this data set, but I got it in January from them. So it might be quite new. I'm using, so they are multi-level data set. I'm using schools, students who were respond in at least one wave, and school with at least 25 of such students in the data. And this left 33 schools, and the schools had school sizes from 25 to 145. And this is the pooled out degree, so it goes from 0 to 10. So you see a nice spread of out degrees. 10 was the maximal number of friends they could mention. And the activities were of two kinds: the sports and which kind of music do you listen to. And these are the out degrees. So number of sports individuals mentioned. The mode is one, so most of them mentioned one sport. Also, most of them mentioned one type of music. And then how many cliques and how many joint activities in the cliques? I used two waves. The maximal clique size was 8, but so most cliques were of size 3. And you see here the number of shared activities in the clique. And you see that most cliques had 0 joint activities. Well, when you think of it, you collect data and somebody may forget to mention a friend, or somebody can forget to mention an activity too. So this criterion of having at least one activity in common for all clique members is really a quite strong criterion. But still, there were a lot with 1 and 2, and even a few with 3 activities in common. Okay, and you see that of the 6 cliques, there were 7 or 8 cliques of size 6 who had 7 or 8. No, there were at wave 2 7 cliques of size 6 who had, where all 6 of them had 1 activity in common. And then we explain this number of shared activities. That's the micro-macro question. And for the 33 schools, these are the counts of numbers. So there are some with 0 and some with an average of one of shared activities. It's not so big. The average of the 33 schools is 40.46, which may not be so large, but could it occur at random? And I will have 3 tests. And first, I will use a permutation test, a quad test, that's based on permuting the friendship network with respect to the 2-mode network. So it's not a process model, but it's just a cross-sectional test based on independent. And then I will be fitting 2 process models, co-evolution models. Well, the first is an actor-oriented model, which is not really co-evolution because it is independent evolution of the friendships and of the leisure activities. And the second uses these to affect the affiliation-based focal closure and the association-based affiliation closure. The QUAP test. So the numbers, here you see the numbers that average to 0.46, and here you see the numbers that were obtained from 1,000 simulations where the friendship network was permuted. And you see that on average, well, you don't even, you see it already that it's very significant. On average, it was 0.26. So the question, could you get this just by chance? It gets the answer, no. And when you do the formal test, you get 8.8 for a standard normal test, which is very significant. For the model with independent dynamics of the friendship network and the leisure time activity network, you get these values, and the average was 0.33 for the independent processes, also much less. The standardized test was 3.5, and also extremely strongly significant. For then the co-evolution model, and let me now give you the example of the results of the co-evolution model. And this is the first part of this is for the friendship network, and this is for the sport and music two-mode networks. So this is just an example which gives you a taste of what is usual for a model for networks of this size: reciprocity, transitivity, degree-related effects, in degree popularity. That means do actors who have, well, I think the nicest to explain here is reciprocal degree activity. Do activity means tendency to send friendship choices. Reciprocal degree, that is the amount of reciprocal ties they've got. And you see the parameter is negative, and the confidence interval is totally on the negative side. So if they have a lot of reciprocal ties, they will tend to be less active, that is, create fewer new ties and more drop existing ties than if they've got fewer reciprocal ties. Quite natural. Also here, same sex, that is, of course, homophily is very significant. Here on the bottom are the two closure parameters. Sport-based friendship closure. When you do the same sports, will you also become friends? Yes. The parameter is 23, confidence interval from 0.40 to 0.33. So the answer is yes. When you have the same music taste, will you become friends? Yes, here also. But for sport, it is stronger than for me. And here are the results for the dynamics of sport and music. And let me focus again on the just on the side. This is a much smaller table because there is less information in two-mode networks than in one-mode networks. So for one-mode networks to model them reasonably, you need more effects. Here are the mixed closures. If you are friends, where you tend to do the same sport as your friend. Yes, indeed. Then will you go to do the same, to like the same music as your friend? Yes, indeed. So there is support for both sides of the mixed closure. Oh, what did I say here? Not that I said, not that having the same music taste. Yeah, well, okay. Okay, that's I'm not going to say, but there is some ambiguity about that. However, This co-evolution model nicely reproduces the number 0.46. Here, the average of the simulated average number of joint activities per clique is 0.45, 0.44. The combined standard normal is 0.3, so that is not significant at all. So this co-evolution model nicely reproduces the macro level property of the number of common activities in the friend group. And now I will continue with a very different example. I know that I've got little time, so I will be quick about that. It is, again, about one-mode, two-mode co-evolution, but it is totally different. It's not a macro question, but it is a question, how is social influence for delinquency structured? And this is delinquency of young first-year secondary school students, so 30-year-olds. I think you shouldn't call it delinquency, but you should perhaps call it naughtiness. And the behaviors in this data set, it's the data of Andrea Knecht, are stealing, vandalism, graffiti, and fighting. At least once, well, I don't know, a week or a month or 2 weeks.
2 months distance between observations.
So in some time. And for fighting, so fighting is rather common, so fighting at least once a month or so, because for fighting the threshold was lower. But they are representative of norm-breaking and say delinquency. Let's call that delinquency. And so is the social influence from friends, is that on the basis, on the level of the general tendency toward norm-breaking, or on the level of individual behaviors? My friend does graffiti, and I go with him, and I also do graffiti. Or is it so that my friend does vandalism, and I will be a non-breaker also, and for example, I will do graffiti or I will fight with him. That can be studied by a one-mode, two-mode co-evolution, because if in the one-mode, in the two-mode network, you can have these four, so it's a two-mode network with 4 nodes in the second mode, these 4. There can be, with the mixed triad closure, the influence for specific items, or with the sum score over those items indicates the general tendency to delinquency. So the sum score will express the general influence at the general tendency. So I use Andrea Knecht's data, and I will briefly picture the effect. So a one-mode type is indicated like this, a two-mode type is indicated like that, and the influence at the level of the sum score has this formula and this sign. So J is a friend of I, and J has a lot of ties to delinquency items. Then I will also have a lot of ties to delinquency items. And for the selection, you get the same. So if J and I both do a lot of delinquency, then they will become friends. And for the same delinquent acts, so level influence and selection at the level of delinquent acts, you get these little triadic figures. These are the results, so 2 pages of results again. And they are quite refined. And here I'm going to focus on the parameter estimates for the cross-network effects, so the effects of delinquency on friendship and the effects of friendship on delinquency. And here in red, I have indicated the significant effects. Classroom average outcome. So the classroom average is the general tendency to delinquency in the classroom. That has a negative effect. That was surprising. And I interpreted this as regression to the mean. In classrooms with a high level of delinquency, it will be in part high because of random influences. So then, since delinquency is not addictive, but is, well, delinquency in these populations is at the level of a normal behavior. So when you are above the average, you will go down to the average. When you are below the average, you will go up to the average, regression to the mean. And how degree friends, so friendship-based delinquency closure, that means so closure and doing the same acts, same delinquent acts as your friend. So there is influence at the level of the individual delinquent acts. And how degree, oh yes, and average friends delinquency, how degree, so the average how degree of your friends with respect to delinquency, that is the influence at the level of the general tendency toward delinquency, that is not significant. So here the result was that in a model where both types of influence were permitted, the clear outcome is that influence is taking place at the level of individual delinquency acts. Okay, to finalize, let me mention a number of discussion points. Although I had to go a bit rapidly, I hope that I've shown you that co-evolution models are really a rich approach with a rich approach to studying context dependence. However, a limitation is that the context is rather small groups. So you've got a network, a delineated network, and when I say small, I would say, well, it could be, if you've got a lot of groups, you could go as much down to 5 group sizes. Or you could go up to 200, but that's the limit of where the model is plausible. I want to say something about the Markov assumption, because the Markov assumption is a very strong assumption that the past doesn't have an effect, but only the present state has an effect. However, enlarging the state space, and for example, with co-evolution models, you enlarge the state space. Also, with we can use ordered networks. So, for example, strong ties and weak ties as an ordered friendship network or association network. Distinguishing between strong and weak ties also enlarges the state space, and that means enlarging the state space means that you reduce the strictness of the Markov assumption. Another point is that I've shown you 2 very different ways of two-mode network of handling two-mode networks. I also showed you multi-level studies, and the first one used estimates for all groups separately. The second one used an integrated Bayesian multi-level approach, random coefficient. So the network is going to be published together with the Swedish researcher Johan Koskinen in JRSS, Journal of the Royal Statistical Society. But both were multi-level studies. I didn't say anything about goodness of fit. However, this is, well, not mainstream, but it is classical statistical modeling, which includes goodness of fit. And goodness of fit, I think, is important here to get credible p-values, because you've got to suggest that you've got a well-fitting model, and to help avoid competing explanations. Because if you don't have a well-fitting model, then somebody might come along and have a better fitting model, which explains it in a different way. And my last remark is that this is definitely not causal in the counterfactual sense. However, the counterfactual approach to causality of Holland and Rubin and Rosenbaum does, in my opinion, not have the is not the only understanding of causality in the social sciences, and this approach gives understanding of processes at a deeper level, and so that is also goes toward causality. With that, I would like to finish.
Thank you very much, Tom, for the excellent overview of stochastic actor-oriented models and for new insights as well. So I will stop the recording now so that people can be more brave